The aim of the experiment is to verify the fundamental frequency of the vibration of a steel bar clamp at the one end is inversely proportional to its length, and to measure the Young's modulus of the material of the bar.
So in the Young's modulus experiment, we have the apparatus that is being displayed here. So this is the Young's modulus apparatus. Before that, we will start from the signal generator itself. So the power is supplied to the signal generator, which will generate a particular signal, and from the output of the signal generator, we are connecting a wire into the power amplifier to amplify the signal which is being coming. So it is connected to the input of the power amplifier from the output of the signal generator. Now the amplified power or the signal needs to be supplied to the Young's modulus apparatus, which is being seen here, from the signal output of the power amplifier to the Young's modulus apparatus. Now if we are coming to the Young's modulus apparatus in detail, so we have a steel rod that is being clamped here, as you can see. So at the end of the steel rod is a magnet. So here on a rail we have an electromagnet kind of thing attached here, so which is being connected to the power which is being supplied. So in the procedure we'll see how the experiment works with this particular apparatus.
Young's modulus, also known as modulus of elasticity, is a ratio of stress to strain. Stress is measured. Stress is force per unit area measured in the Pascal, and strain is ratio of original deformed length to original length. And this, by Young's modulus, we can figure out how extent material can compress or stretch under the influence of a force. The stiffer the material is, then Young's modulus will be more.
So through this experiment we are trying to find the Young's modulus of the material chosen, right? So we have the Young's modulus formula which is being derived after the particular theory. So y is equal to 4y square divided by 1.845, which is factor to the power 4 into 12y by d square times alpha square. Now we'll see what this term means. So y generally denotes the density of the material which we are choosing, and d denotes the thickness of the material which is being chosen, and alpha is the slope of the graph between L square and 1 by f, which we plot after recording the values. So in the procedure of the experiment, initially the bar which is being seen here is adjusted so that the length from the tip to the hooking point is 20 cm. Now the excitation coil which is being connected to the power is almost at a distance of 1 cm from the coil and the bar. Now the signal generator which you can see is set in the range of 10 to 100 using the knob which is being present here. Then after setting that, the signal generator and the power amplifier are both turned on. Now the amplitude knob on the signal generator is slowly turned to the right till the stable reading of frequency at 9 Hz is shown in the display. So almost we are getting in the range of 8 to 10. So since it is not stable, we are getting a range from 8 to 10. After setting this, the output amplitude as seen on the panel meter of the signal should be of the order of 1.5 volt. So since it is in the range form, we are getting almost in the range of 1.5 to 1.9. So now what we are going to do is the basic apparatus, the experiment starts from this point. So now we'll rotate the frequency knob, and at one point, if you're seeing the apparatus, the rod should start vibrating with the maximum frequency. The maximum frequency should be associated with the length of the rod, length of the clamp which we are setting here. So at that particular frequency at which the rod is vibrating the maximum, we'll just denote it as the fundamental frequency for that particular length. Now we'll turn off everything and then adjust the length by 2 cm or 1 cm, preferably 1 cm, till 16 cm, and for each length we'll measure the fundamental frequency using the same procedure as was detailed. So for different length of the steel bar which we have already found out from the experiment, we have found the resonating frequency. So after finding the length, we just square it in the SI units, which is in the meter square. Then with the frequency, you just take the inverse of the frequency, which will be 1 by f. Now after taking the values, what we are going to do is we are going to plot a graph between 1 by f, which is in the x-axis, and L square, which is in the y-axis.
From the graph of L square versus 1 by f, we will find the slope, which is equal to 0.534. We will substitute this in a Young's modulus equation, which we already know, that is 4 pi square by 1.8754 to the power 4 into 12y by d square into alpha square. For a given material, we took y is equal to 85,000 kg per meter cube, and d which is thickness of the material, is equal to 0.9 into 10 to the power minus 3 meter. We will substitute this in a value and a slope which we obtained from the graph. After substituting this from the calculation, we will obtain approximately the Young's modulus is equal to 115 gigapascals.